about how Ptolemaic astronomy should be improved. Now, Al-Farisi's specific problems or questions were to understand the refraction of light. And he studied Ibn al-Haytham's treatise on optics very closely. That's the treatise where Ibn al-Haytham develops his theory of vision, the intramission theory of vision. And Al-Farisi actually produced his own revision of Ibn al-Haytham based on his own experiments. Now that's how science, of course, advances. Every generation tries to correct the generation before, and that's what happened here. Now the explanation of the rainbow was Al-Farisi's best known achievement, which also required a revision of Ibn al-Haytham's theory of colors. Ibn al-Haytham had proposed that the rainbow was produced by sunlight reflected from a cloud. Al-Farisi's model has the sunlight being refracted twice within the body of water droplets. To discover this, since the actual situation could not be investigated directly, he ingeniously constructed an enlarged model of a raindrop consisting of a glass jar filled with water. He then placed this raindrop model in a camera obscura of the kind that Ibn al-Haytham used so that he could control the amount of light that he projected into the jar. He was able to demonstrate that the rainbow spectrum of colors is produced by the decomposition of light through refraction. So refraction occurs because the different colored light has different wavelengths and therefore bends at a different angle when passing through a different medium. And in the case of the rainbow, the water droplet, as Al-Farisi demonstrated, actually produces two refractions of a light ray. In each case, or when it enters the water, and then when it leaves the water, including a reflection at the midpoint. And by the time the light leaves the water, the colors are refracted to the point where a rainbow spectrum is produced. Now, he also demonstrated that a secondary rainbow was produced through the same process, through an additional circuit of reflection and refraction. Perhaps you've seen the double rainbow effect in actual experience. Notice that the colors of the second rainbow are in reverse order. Al-Farisi demonstrated that as well. Now, this experiment is similar to the researches later conducted by René Descartes and Isaac Newton, although Newton famously used a prism rather than a jar of water. Also, in one of those coincidences of parallel discovery that were not uncommon from the history of science, an older contemporary of Al-Farisi's in Europe, Theodoric of Freiburg, a Dominican friar who worked in Paris, he conducted a similar experiment and reached similar conclusions. There was, however, no contact between these men, and the only thing they had in common was that they both studied Ibn al-Haytham's optics very carefully. Now, for my last instrument, I want to talk about the Islamic astrolabe. I want to show how another Persian scientist named Al-Biruni used the device to determine the circumference of the Earth to begin with. And then I want to talk briefly, give a brief overview of what the astrolabe actually is in terms of being an instrument. The astrolabe actually is a model of the heavens, and it's used for telling time, calculating prayer times, and determining the heights of objects, which is what I want to talk about now. So Abu Rayhan Muhammad ibn Ahmed al-Biruni died in 1048. He was one of the greatest mathematicians, astronomers, and geographers of the Islamic world. He spent most of his career as a captive member of Mahmud of Ghazna's court, which involved several expeditions to India. And during those expeditions, al-Biruni studied Hindu customs, Hindu science, mathematics, and wrote a masterful treatise on the description of his experiences there and a description of Hindu culture. Now, using the sighting tube on the back of an astrolabe, I don't know if you can see, this is my working model, my teaching model of an astrolabe. That's the front with all the parts that I'll talk about in just a minute. On the back, there is this piece called an alidade. And on a real astrolabe, it has a sighting tube that one can line one's sight up from one end of the alidade to another and use it to determine the elevation of a star above the horizon, or to determine the height of a tower, say a minaret of a mosque, or the height of a mountain. And so al-Biruni used a device like this to determine the height of a distant tall mountain from two observations. These observations were spaced apart by a distance d. So taking these two observations, these two angular results, and putting them together in the trigonometric formula to the right, the height of the mountain could be determined. Now, once the height of the mountain was determined, then using some more trigonometry and one additional measurement, the angle alpha, which is the angle from the angle of the height of the mountain from the horizon, he could then use this formula in the yellow to calculate the circumference of the Earth. And the result he got was very, very close to the modern figure. Quite ingenious use of instruments. Now, the astrolabe, I said, was an analog computer and a portable model of the cosmos, which can represent the positions of the sun and major stars at any time of the day or year for a given latitude. The astrolabe on the right is a famous astrolabe which belonged to a ruler of Central Asia, the famous Ulugh Beg, who lived in the 15th century, who built the famous observatory at Samarkand. He himself, although he was the grandson of Tamerlane, one of the bloodiest conquerors of all time, he was a peace lover and mathematician and astronomer. Astrolabes also were important for the transmission of scientific and mathematical knowledge from Islam to the West. This little device carries a ton of mathematical knowledge in it. A lot of complicated calculations are reduced to simply moving dials and parts and lining things up with and determining results. The Islamic world is also noteworthy for developing other kinds of instruments, like this complicated computer, which determines the Qibla direction to Mecca, the direction that Muslims must face when praying, which is a complicated problem in spherical trigonometry, but here it's been reduced to an analog computer. So the astrolabe, as a model of the heavens now, has several parts I want to talk about in brief. I don't know how well you can see this. Oh, maybe I should get out of the...
Yeah, if you would like, you can actually just stop the screen share to show us the astrolabe and then bring it back when you want to show the components.
Okay, so how do I do that?
So at the bottom where you started the screen share, at the bottom of the screen, yep, there you are.
Oh, okay. All right. And then how do I get back to me? Or can you see me now?
Yep, we can all see you perfectly fine.
Okay, but I can't see what I'm actually showing you. Is there any way that I can enlarge my image?
Yep, we have it enlarged, so we only are seeing your face on the screen.
Are you seeing the astrolabe?
Yep.
Okay. But I can't actually see very well of what I'm showing you. That's the problem.
So if you look at in the top right-hand corner where
Yeah.
you have gallery view or
Yeah.
speaker view, you would press on
Okay, that's
speaker
better.
view.
That's
There
better.
you
Thank
are.
you. Okay, thanks. Okay, so what we have is a coordinate system on the front of the astrolabe. You can probably see those curves that look in a crosshatch pattern. Those represent the sky above the horizon. That's a way of locating the sun and the stars as they appear in the sky. The line here along the bottom is the horizon, and up here we have the zenith. Here we have the meridian line, and so one can trace the path of stars or the sun from when they rise in the morning across the sky, across the meridian at noon, and all the way down to when they set. And then if we take a measurement of a star or the sun, we can line up this moving part to place the sun or the star in the appropriate position in the sky, and then we can read the time from the side. For example, I need to know where the sun is in the zodiac. This is the zodiac coordinate system representing the sun's longitude throughout the year. I need to find where the sun is for a particular day. Let's say it's at Scorpio 10, for example. Then to determine the time of sunrise, I take Scorpio 10 and I line it up with the horizon, which is where the sun actually rises, of course. So I have these two curves, the horizon, Scorpio 10, representing the sun, and I line my rule up with that, and then I can read the time off the side of the astrolabe. I can use this device any time of the day or night. During the day, I would need to determine the altitude of the sun, which I can do not by looking at the sun, of course, don't go blind, but there's a way of using shadows, shadow lengths. You determine the ratio of your shadow length to the length of the stick that you're using, and there's scales on the back of here which enable you then to determine the angle of the sun. So you line up the ratio of the scale, the ratio of the shadow to the stick down here, and you can read the angle of the sun off of here. Once I know that, then going back to the front, I take Scorpio 10, which represents the sun, and I line it up to the coordinate line representing the altitude of the sun, whatever I determine. And then I take my rule and pass it through the sun, and I can read the time off the side. To do this at night, of course, what I would do is I would pick a bright star, and the rest of this front piece has stars on it. I pick a bright star. I would use my sighting tube to determine its altitude. Then I'd go to the front. I'd line that star up to whatever altitude I determine. Then at night, of course, the sun is below the horizon. So, and you can't see it, obviously. So I take my rule and I line it up with wherever the sun is, and I can read the time from the side down here. Now, the astrolabe has several other fascinating properties. One of them that I like to use to show students how to use it is to determine the Muslim times of prayer. The 5 times of daily prayer can be determined quite readily with the astrolabe. Let's see if I wanted to cover anything else. I'm going to go back to shared view for a moment. There we are. You can actually make your own astrolabe quite easily. There are computer programs available online that will generate the plates for you. Here's the one I use. Will generate the plates for you, which are the front plate is useful only for a specific latitude. If you change your latitude, you have to have a different plate because it can vary. See, this is on the left we have the plate for London, which is about 51 degrees north latitude. And on the right, we have the plate for where I live in Claremont, California, which is about 34 degrees north latitude. And you can see the difference in the curves. Just quickly, the piece that I was moving on the front has the stars and the representation of the sun on it. You can think of the astrolabe as a clock in the sense that the sun would be at the tip of that red arrow as it then moves throughout the day. The ingenuity of the astrolabe is derived from the fact that it's actually a squashed sphere. It's like the celestial sphere has been squashed down into a plane, which makes it much more durable and actually much more useful and easier to construct than a sphere. So what I was doing on the front of the astrolabe with those coordinates is actually what an astronomer does in a three-dimensional coordinate system. It's just that the coordinate system has been squashed into a plane. Anyway, let's see. Yeah, so here's the 5 prayer times. They are mostly, well, they're all determined by the position of the sun, whether it's dawn, sunrise, noon, or specific shadow lengths that must then be calculated using the astrolabe, but can be done quite readily. Now, a timekeeper like Ibn al-Shatir would have done these calculations more precisely using trigonometry, but if you're stuck in a pinch and you don't have either mathematical skills or you don't have the time to go through all of that, you could simply use your astrolabe to figure out, well, the times that you're supposed to pray today, for example. And some astrolabes actually have markings on the back. On the upper right of this astrolabe, it shows the time of the afternoon prayer, which is a little bit more complicated. Instead of doing the complicated calculation, one can simply line the device up along those curved lines. Okay, let's see. So, what I hope I've been able to demonstrate is the great ingenuity of Muslim scientists in the use of instruments to investigate nature and to advance our knowledge of the natural world. Thank you.
Hi, Dr. Glenn, we actually have some questions for you.
Okay.
From Facebook. So one question says, were astrolabes used by the general public or just astronomers? They seem complicated.
They could be used by anyone. They are complicated, but they're much more intuitive than actually doing calculations with trigonometry. Astrolabes were used in education, so they would have been used by teenagers and college students in the Islamic world and in Europe to learn basic principles of astronomy. The chief obstacle was that they were expensive, and the really nice ones were made of metal and, of course, very expensive. Now we have reports of some astrolabes being made of wood and paper, but those have not survived. So,
hey.
Yeah.
Very cool. This is a more personal question for you. How did you originally become interested in this field?
I started off in mathematical physics, and I was specializing in Einstein's general relativity. So I was interested in astrophysics and astronomy. And then I went to England for a year and studied philosophy at Oxford. And I kind of got more interested in the history of science rather than the practice of science. And so it took a few years to realign myself, but I'm also pretty good at languages, and I decided to study Greek and Arabic, and that's how it happened.
Very cool. And another one for you, again, more about yourself. So what do you wish the world knew more about this area? Let me reread that for you. What do you wish the Western world knew more about in this area?
I wish that my fellow Westerners could appreciate the foundation of modern science, or one of the foundations of modern science, being located within the Islamic world. We tend in the West to think only of our Greek and Roman cultural and scientific forebears, and we forget about the Muslim advances in the sciences. I would like that to be more recognized by my fellow Westerners.
And this question appeared a few times. The astrolabe looks familiar. Is it in the opening scenes of Game of Thrones?
I don't watch Game of Thrones. It probably is. Sometimes the astrolabe is used in programs like that to evoke some of the technical and scientific sophistication of the medieval world. So I wouldn't be surprised.
Thank you so much, Dr. Glenn, for talking with us today and answering our questions. You had some amazing content to share with us, and you have a good evening.
Thank you.
Great, and everyone else, if you'd like to see more and learn more about 1001, please do come to the Michigan Science Center. Our exhibit is free with general admission, so stop by and join us. Thank you so much, and everyone have a great night. Bye.
Bye-bye.